Okay, guys, welcome. Today, we're going to talk about the section where that's titled How Numbers Can Deceive, and we'll look at polygraphs, mammograms, and more. All right. So in a lot of cases, you can have numbers sort of be slightly deceiving because they don't truly reflect the results of an event, right? So if you sort of analyze numbers under certain conditions that seem normal, you can sort of be led astray from what's actually going on, right? So for example, let's look at this table, right? So the table gives the shooting performance of two players in two halves of a basketball game. Now, if you look at these two players, you have Kevin and Kobe, right? So Kevin had a higher shooting percentage in each half, 40% and 75% over 25% and 70%. Now, does this mean that Kevin had the better shooting percentage for the game? All right, well, let's take a look. Now, if you look at the entire game, right, the field goal attempts for Kevin would be 10 from the first half and 4 from the second half, so 14. Now, how many did he make? Well, he made 4 in the first half and 3 in the second half, so 7. So field goal percentage was 7 for 14, which is 50%. Right? Now, if we look at Kobe, in the first half, he attempted, let's see, so he attempted 4 shots. In the second half, attempted 10. So he also attempted 14 shots. But if we look at the field goals made, we're going to have 1 plus 7, so we get 8. Right? So we're actually going to get 8 for 14. Right? Which let me just calculate it real quick, just so we have a specific number in there, is going to be 57.14%. Right? So even though Kevin had the better shooting percentage in each individual half, right, which seems like a logical thing to look at, overall in the game, he actually had the worst shooting field goal percentage. All right, so that's one quick example of how numbers can deceive. All right, let's look at another example of how that can happen. Now, in the early 1970s, a medical study in England involved many adult residents from a district called Wickham. All right. Now, 20 years later, a follow-up study looked at the survival rates of people from the original study, and the follow-up study found the following surprising results. Right. So among the adults who smoked, 24% died during the 20 years since the original study. Right. Now, among the adults who did not smoke, 31% died. Right. So do these results suggest that smoking can make you live longer? And of course, the answer here, of course, should be no, right? And the idea is that there could have been other things going on. Maybe the smokers could have all been younger, been generally younger than non-smokers. Right? There could have been underlying health conditions. There could have been other factors. There's many different factors, but the most realistic one is probably the smokers were all generally younger. All right. So we don't have the complete picture just given from this example. So the way that this is worded might lead you to the fact that smoking would make you live longer, which of course we know is not true. Okay. Now, the next sort of type of way that numbers can deceive is illustrated by the following. Right now, oftentimes there's many different health screenings that you can get to predict a medical abnormality, right, with a certain percentage of accuracy. So, for example, a mammogram test may be 85% accurate. So it will tell you that 85% of the time correctly, a tumor is cancerous or benign, right? However, if you get a positive reading or a negative reading, you might be misled because the actual chances are still about 5%. And we're going to see an example where that is true. Okay. Now we're going to consider a study in which mammograms are given to 10,000 women with breast tumors. Now, we're going to assume that we know that 1% of tumors are malignant, all right? Now, 1% of 10,000 would give you 100, right? So we know that for the tumor is malignant, we're going to have 100 total, right? Because that's 1% of 10,000, right? So then, of course, the remaining 9,900 would have benign tumors. Now, if the test is 85% accurate, out of these 100, where the tumor is malignant, 85% of 100, or 85, will be correctly identified as malignant. But the other 15 will be incorrectly identified as negative, right? So we call those false negatives, right? Now we also look at 9,900, and this is also 85% accurate. So 85% of 9,900, which would be 8,415, are going to be correctly told that it's actually negative, right? But then the remaining 15%, which is the 1,485, will be incorrectly told that the tumor is malignant. And we call this, of course, a false positive. So now in total, there are 1,570 positive mammograms and 8,430 negative mammograms. And now we're going to answer some questions regarding this. Okay. So let's see. So that's what this is. Yeah. And then here's sort of what I talked about. The mammogram would give 1,570 positive readings, only though 85 are actually malignant. So if you do 85 out of 1,570, you get 5.4%, right? So even though you had all of these positive results, only about 5% of them, of course, are accurate, right? So based on the table, what is the percentage of women with negative test results who actually have cancer? So false negatives, right? So 8,430 had a false mammogram. I shouldn't say false, I should say negative. Right? But there are 15 that actually have it out of that group, right? Because we're looking at all the negative ones. So we're looking at these three pieces of data. Right? So if we do 15 out of 8,430 and multiply that by 100, we would get that if you test negative, there's still a chance that you have it. And in fact, that chance is 0.1779%. Right? So it's not a great chance, but it's still a chance nonetheless. It's still it's a non-zero chance, right? So that's one thing to keep in mind. All right, so now we're going to set up a similar type of problem where we're going to actually create this table from scratch. All right. Now, all athletes that are participating in a regional high school track and field championship must provide a urine sample for a drug test. Those who test positive for drugs are eliminated from the meet and suspended from competition for the following year. Now, studies show that at this particular laboratory, we have a 95% accurate test. So let's write that down, 95% accurate test. Right? And that 4% of all athletes will use drugs. And then the question that we're going to look to answer is what fraction of the athletes who fail the test are falsely accused and therefore suspended without cause. All right, and we're going to assume that there's 1,000 athletes in the meet. So let's make a table just like we have before. So let's set that up first, actually. Okay, so if we have a use drugs column and a do not use column, and then we put in our test results, so test positive, and test negative. and then put in our totals. Well, we know that 4% of athletes use drugs. And if we're using 1,000, then I need to take 0.04 of 1,000, which would give me that 40 total are going to be using, right? Now, if this test is 95% accurate, it's going to correctly identify 95% of 40, which I believe is 36, but let me just double check that. So if we do 0.95 of 40, 38, sorry. So we get 38, right? And then of course, the part that would test negative, we would take 5% or 40, which better be 2, right? Because if I add 38 and 2, then that would give me the 40 total. Now, of course, if 40 do not use drugs and there's 1,000 total, that means that 960 do not use drugs, right? Because then that would give us the 1,000 total. And of course, the test is going to correctly identify 95% of that 960, which would give us 912. And then 5% of that, which would be 48, sorry, 48, right? Would be false positives, right? So it looks like the total that would test negative would be 914, and the total that would test positive would be 38 plus 48. So then that would give us an 86. Okay, now we can answer our question. Want to know what fraction of the athletes who fail the test, right? So fail the test means that they test positive. So we're looking at 86. So what fraction of the athletes who fail the test are falsely accused, right? So 48 of them do not use. So we would have that 48 out of the 86 that tested positive, so do not use, out of tested positive. This would be the fraction of people that are falsely accused. So if we do that, if I do 48 divided by 86, that would give me, times 100, of course, about 55.8%. So over half of the people that tested positive are not using and therefore would be falsely accused. All right. So that's how these numbers can sort of be deceiving here, is because now you're getting a large percentage that are falsely accused. Right. And that's why a lot of times you hear about these lie detector tests that may be very accurate, but you're still going to get a large proportion of people that are falsely accused, which is the basis why they're not permissible for evidence, like in court cases and stuff. Okay, so to finish out this, we'll talk about a couple more examples where numbers can be deceiving. And in this example, we'll talk about how in politics, politicians use statistics that work well for them, right? Now, of course, they could be accurate, but they might not tell the entire story, right? So we're going to look at that right now. Now, government spending for a popular education program was $100 million last year, let's just say. All right. Now, when Congress prepares its budget for next year, spending for the program is slated to rise to $102 million. Now, lobbyists immediately go into action because those who support the program complained about the planned cut in the program, while if those that oppose the program, saying that it should be increased when it should be cut, or saying that it is being increased when it should be cut, right? Now, the reason why both sides are technically correct here is because the program is rising by $2 million. However, $3 This should say CPI. The CPI is expected to rise by 3% over the next year. So if you take 3% of 100, you should be increasing by 3 million, right? If you were to rise with inflation. So it is not rising as fast as inflation. So the budget, even though it's being raised in actual dollar amounts, it's being lowered in the dollar amounts for each respective year, right? So sort of based on a CPI standpoint. So even though, again, the program is rising in an absolute sense by 2 million, it's not rising as fast as inflation, and therefore it's essentially losing value in the next year. So that's what we sort of mean by that. All right. So that concludes this video on how numbers can deceive. I hope you enjoyed, and I will see you next time.